This is section 4.1, more nonlinear functions. And we're going to look in this section really at polynomial functions. Underneath this title here, it says the domain of a polynomial function is all real numbers. That means it can be any x in the world. Its graph is continuous and smooth without breaks or sharp edges. In a polynomial function, the degree is the highest exponent. Okay, so as we look at some of these examples that I've written here, f of x equals 10. That is a polynomial function. And if you're asked about the degree, you're looking for the exponent. We don't even have an x. There is an understood x to the 0 because anything to the 0 is 1, and 1 times 10 would be 10. So when you look at that, then you can say that the degree is 0 and the leading coefficient is 10. All right, in g of x equals 2x minus 3, what is the degree? The exponent is understood. We don't see that. And so we know now that the degree is 1. The leading coefficient is the number attached to that x with the highest exponent. So our leading coefficient there is 2. In this one, even though they're not in order, here's our highest exponent. So our degree is 2, and the leading coefficient is 3. I don't know what that red there is. That should be -1/2. Okay, so the degree of this one is 6. That's the highest exponent, and the leading coefficient is -1/2. Now we need to put in here, add in a couple of things. The exponents in the polynomial cannot be negative, fraction, or radical. Okay, that would keep it from being polynomial. So in a couple of your homework questions, it will ask you, is this a polynomial? And if you saw a -4 there, if you saw 4x to the 1/2 to the 2/3, or if you see a radical up there, that keeps it from being polynomial. All right, in these polynomials that we're going to look at, we're going to talk a lot about the absolute min, max, local min. And this is a nice little chart that just kind of brings it all together for us. All right, so in this one, we do have an absolute min. That means it's the very lowest point of this graph. In this case, it is -6. That's the y value. Absolute max, there is none. This is going on forever. In this picture over here, the absolute highest point is right here, so the absolute max is 12.7. The absolute min, we don't have one because this is going down forever on both sides of this graph. A local max, that means right here is somewhere in this graph where it's a high point. It changes from increase to decrease. So there's your local max, 2.25. A local min would be right here. Okay, so those are some terms that we'll be looking at. We're also going to look at symmetry. And we'll talk about even and odd functions. Even functions, example, x squared, x to the 4th, x to the 6th. Notice all the exponents are even. Those are even functions, and they are symmetrical with the y-axis. That means they are the same on either side. If you folded it, you'd get the same shape. So this we know is x squared. It's probably x squared minus 1, but it is an x squared function. And there's some other things here that are even functions, and you can tell that because they're symmetrical about the y-axis. Odd functions are symmetrical with the origin. And what that means is if these graphs are spun around 180 degrees around the origin, then they match. So in other words, if you took this piece and you did it 180 degrees around, you'd get this piece. Does that make sense? So they don't look quite as obvious as the even ones in their symmetry. This one is about spinning 180 degrees and you end up getting the other piece. All right, so I think that's all the notes. We should be able to get started on our problem set. Let's go back to the start here. And we start out saying, you know, are these polynomial functions? If they are, state the degree and the leading coefficient. So, is this polynomial? Yep, no problem with the exponents. It does look polynomial, so we're going to choose that. It says, what's the leading coefficient? There's no number in front of the x squared, so that's going to be a 1. It's understood. And the degree is 2. Next one. And we want to remember that the 6th root of x is the same as x to the 1/6. There's an understood 1 there, and there's your numerator, there's your denominator. And now we have a fractional exponent, so that keeps it from being polynomial. How about this one? Absolutely no problem there. It is polynomial. The degree is 5, and the leading coefficient is -6. All right, number 4. Number 4, when you have an x in the bottom of a fraction, for you to bring it to the top, it would have a negative exponent. So anytime you have x down here, it's not going to be polynomial. All right, now we're going to talk about that local extrema. So we are saying, where are the high and low points? So we have 1 here. What's the y value there? 4. We have a low point here. What's the y value? That's 1. So our local extrema would be 1, 4. That is looking for the y values. Let's look at number 6. Determine any local and absolute extrema. Now with this one, you're going to need to put it in your calculator. This is good practice for you. Let's go to y equals, clear out whatever is there, x squared plus 3x minus 4 Now on that one, I cannot see what I need to see because I'm looking for the min. So I do need to change my window and my y min. Let me do a zoom 6 and see if I can get it. There we go. All right, so if you want to find the min, remember second calc, min is number 3, and you want to go over till you are on the left of the lowest point and hit enter. Move over to the right of the lowest point and hit enter, and enter a third time. And so you're looking for the y value, and it's negative 6.25. It asks if there's an absolute max. There wasn't because we had this picture. All right, so that's going on and on forever up this way. So we would put an n there for that. All right, let's look at number 7. Using a graphing calculator, estimate the local maximum of this. So let's do the same thing. Let's go here and we will put in, we'll clear that one, and we have an x caret, here's your caret key for to the third, so caret third x to the third minus 1.5x plus 1. All right, we'll graph. All right, so it's asking for any max and min. And just to be able to see these a little bit better, I'm going to do a zoom 4. All right, so I'm going to put that picture over there just so we'll be able to mark on it. But let's find this max here. Second calc max. All right, and we'll go over here to the left of that high point and hit enter. Over to the right of it and hit enter and enter. And we have 1.707. It does say round to the nearest thousandth. That's 3 places. So if you round wrong, it's going to count it wrong. Be sure that you read those directions. So that was that one. Now let's get that back and let's find this min. Second calc min. And let's go to the left of the low point, enter. To the right, enter. And enter. And we get 0.928. We're going to round up, so we're going to have a 0.293 for that one. And so just remember, you were finding that point and that point. And just be sure and read directions for the rounding. All right, let's see if this one is polynomial. Note we have an x to the -6. So that exponent keeps it from being polynomial. Okay. Number 9, use the graph to estimate the local extrema and absolute extrema. Hint, here we go. Local extrema cannot occur at endpoints. Okay, they'll only occur on open intervals. So, a local extrema. Are we going to have a max here? We're not going to have a local max because those are endpoints. It just told you that. But we do have a min. And so the min, we're looking for the y value here. What's the y value? -4. And then it asks you about the local max. And there is no local max, or there are no local max. The next part, and I don't know if I can keep the picture there. Let's read this. Estimate the absolute min of f. All right. Is our local min also our absolute min? It is. So that's still at -4. Estimate the absolute max. Okay. So if it's an absolute max, it can be at the endpoints. This was just about local. So what is the absolute max? It's that point, and we're looking for the y value. And if we look down here at our choices, I'm not sure I would have guessed 7.7 exactly, but since that's one of our choices, it was 7 something. So we knew that that was going to be the right answer. Okay? All right. Let's look at number 10. List the values of x at which f has a local min. All right, so we're only worried about the x values. All right, a local min. How many mins do we have? Let's look here. There's a min, there's a min, there's a max, there's a max. And it's asking about x values. So 1, 2, 3. This one's -3. This one's at 1. Okay. All right, so up here, that would be -3, 1, x values. The values at x for which f has a local min. What are these local min if they exist? That's wanting y values. All right, so at this one and this one, what's the y value? They're both at y equals -1. So that's what we would put for that one. Number 11, local extrema for this one. And you would put this one in your calculator, just like we did on the others. We'll clear this, really good practice for you. X squared minus 4x minus 5. And we'll do a zoom 6. And we'll find the min. Second calc min. We'll hit enter. And then we'll move over to the right. Enter and enter. And the min is -9. And is there a max? Absolutely not. So -9 here and no for that. Now we're going to look at some graphs and tell whether they are even, odd, or neither. So on this one, this is not symmetrical about the y. It's not symmetrical about the origin, so this one is going to be neither. All right. Discuss the symmetry of this. So I don't know if you can see that really well, but it's doing this. It's kind of flat down here and doing that. That is symmetrical about the y-axis, and that makes that function even. Can also tell that because of the two exponents, the 6 and the 8. All right, 5x. There's no picture for that, but what's the understood exponent? It's a 1, which is an odd number. This is an odd function. All right, on number 15, 4x plus 2. And at first glance, you know, you have that 1 there. Let's think about what this graph looks like. 4x plus 2. So that means our y-intercept is at 2. And then we're up 1, 2, 3, 4, and over 1. And up 4 and over 1. So our line goes through there. It is not symmetrical around the y-axis. It's not symmetrical about the origin. It is neither. How about this one, number 16? That is even, because you've got the x to the 4th minus x to the 8th. And you could put it in your calculator and you would see that as well. How about number 17? X to the 8th plus x to the 5th. You got one even, one odd. That's going to make that one be neither. All right, number 18 is a graph, and we're going to do some analysis, and may need to make this a little bit bigger for you to see, but you'll be seeing it on your lecture notes. The graph shows the temperature readings in the sun X hours past noon. So here's the hours past noon, and here's your temperatures. A part, the absolute max is, so that's what is the y value that's the highest point. So here we go, and we're right here, and that would be at 83. It does say round to the nearest whole number if we don't end up on a whole number. The absolute min is right here, and we're in between 77 and 78. And we're closer, so I believe that's going to be a 78. Which of the following is the correct interpretation? The absolute max indicates the average of all local max. No, that's not about average. The absolute max indicates the highest temperature, and the absolute min indicates the lowest temperature. That is true. The local max and the local min are. All right, the local max. We have two maxes that aren't at the end point. One was this 83, and this one is at 80. So I would say that would be 80, 83. And the local mins, we've got one here and one here. And so that was at 78, and this one is at 79. Okay. All right. And which of the following gives the intervals for which the temperature was increasing? Well, let's see. It was increasing from here to here, and it was also increasing from here to here. So those are x values that we talk about. So which one would that be? Looks like this is 1 point, it's about halfway, so maybe 1.6 to 2, here would be 3, 2.7, that seems right, and from 3.7 to 5, yes, so this is it. You're just going to have to look at them and check and see, but that actually does fit with our picture. Number 19. This graph approximates the monthly temperature in degrees Fahrenheit in a particular city. In this graph, X represents the month where X equals 0 corresponds to July. So here we are. Here's July. These are the months leading up to July. These are the months after July. And here's our temperatures. Is this graph odd or even? Well, it's symmetrical around the Y, so this is even. All right, June corresponds to X equals -1 and August to X equals 1. The average temperature in June is 83 degrees. So the average temperature in June is 83 degrees. The average temperature in August is, well, let's look here at June, we're here, and here in August, we're at the same value. So we would have 83 degrees. May corresponds to X equals -2 and September to X equals 2. According to the graph, how do their average temperatures compare? So we're looking at May and September. So we're here and we're here. So your choices would be equal to, less than, more than. Well, it's equal to. I think that'll probably be a pull down box. Interpret what this type of symmetry implies. Well, if you read through them, the average temperatures of the corresponding months are equal. Okay. And 19, our last one, we're still doing this. Is this continued? Yeah. Sorry. Oh, did that just get written on there twice? Oh, it so did. Okay. Well, I'll take that one off. So you only have to do that once. All right. I think that will get you through 4.1.